Thank you very much for joining. We got the session right after or during lunch. If you're in the East Coast of North America, and there is a lot of great content to choose from. So I certainly appreciate that you decided to join this session. We are going to be talking about decentralized artificial intelligence, which is a session at the intersection of a few of my passions: artificial intelligence, of course, blockchain, cryptography. So the session is very deep, technologically speaking, but it also incorporated some aspects of economics, some aspects of philosophy. So hopefully you'll find it well balanced. I'm Jesus Rodriguez, by the way, so I'm going to switch off to the slide deck. So let me just tell you a little bit about myself. As I said, I'm Jesus Rodriguez. I'm the founder and chief scientist of a company called Invector Labs. So you can think about Invector Labs as a next generation consulting firm with two main caveats. So we focus exclusively in deep technologies. So think about blockchain, artificial intelligence, cryptography, Internet of Things, that type of thing. And also we leverage a very high-end talent network of freelancers all over the world. So we have this network of experts in all these deep tech areas, and then we work with big companies, mostly in North America, and we assemble teams dynamically to work on projects. So because of the nature, we sit at a very weird area of the intersection of academic research and industry. So for instance, this first talk about decentralized AI is very research oriented, even though I'm going to give you some practical tips about companies doing this. Today, my second talk is all practical about how to build deep learning solutions at scale. I do a lot of speaking engagements and writing. I'm an investor in over 12, 15 different enterprise software companies and sitting like 6, 7 different boards. And that's all you're going to hear about myself and Invector Labs, because we're here to talk about decentralized artificial intelligence. So here's a high-level agenda. We're going to talk about the centralized nature of AI and some of the problems, and then the risk and promises of decentralizing artificial intelligence. And we're going to deep dive into some what we call foundational blocks of decentralized AI solutions. So we're going to cover some security trends like homomorphic encryption, GAN cryptography. After this session, Ian Goodfellow is going to be talking about GAN, so I think this is a good intro. Secure multi-party computations, federated learning, blockchain technologies. And then to not keep things in the theoretical aspect, I'm going to be talking about 4 or 5 platforms that are doing this today and give you some practical tips about how to use it. And hopefully that will round up a good talk. Again, if you have questions, feel free to use the chat during the. I think we can monitor it and stop for questions any minute. So decentralized AI is a topic very dear to my heart. At the beginning of the year, I wrote this 3-part essay about decentralized artificial intelligence that covers economic perspective, technology, and the current platform. So a lot of the content in this session, you're going to find it there. And recently, I published another article about the challenges of AI, the centralized nature of AI. Again, this talk sort of summarizes a lot of those concepts. So the thing with decentralized AI is that it's very complex, it's very new, but there is also a lot of hype about it. And the hype has mostly been driven by the race in cryptocurrencies and blockchain technology. So with the popularity of those technologies, many people start thinking about the intersection of blockchain and AI, and that decentralized AI is just a fact, when in reality it's very complex to build, if not only complex, but practically almost impossible today. So how does hype look like? Well, you have our publications like Forbes talking about the benefits of combining these two trends in several articles. You even have this startup that combines cannabis, artificial intelligence, and blockchain, and somehow the website has this green figure with a weird eye. So it seems like a good investment. just because of the trends. Right, so there is a lot of hype about this space. The reality is way simpler than that. Why should we consider decentralized artificial intelligence today? So one example is mobile and IoT devices. We have a ton of devices, billions of devices executing artificial intelligence models all the time. So executing those on a centralized manner is really complex, if not completely impractical. The other thing is we have decentralized architectures are here to stay. That's a fact. So many people call it Web 3.0, but the fact is that blockchain technologies was a major breakthrough in computer science, and whether you like it or not, or you agree with the approaches or not, the promise of blockchain is materializing across several industries. There is this brilliant, absolutely genius post of Chris Dixon, a partner at Andreessen Horowitz, titled "Why Decentralization Matters," that explains why this type of movement is almost inevitable, and almost all technology trends will transition to certain level of decentralization. Now, let's look at this from an economics perspective before we deep dive into the technological aspects. So if you follow, Carlota Perez is a researcher at the London School of Economics and one of my favorite economists. And she wrote this book back in the early 2000s called Technological Revolutions and Financial Capital, in which she explains the evolution of capital across technology revolutions from the Industrial Revolution to the internet, right? And there are many, many, many lessons in that book. It's a very deep book. But one of them is that technology movements tend to go from technology and economic movements, like we can classify artificial intelligence on both of those trends, tend to go from a very centralized movement to completely decentralized to a certain level of re-centralization. And for instance, an example of that could be after the collapse of the Soviet Union, almost every Russian citizen received shares in the Russian company, so that went completely decentralized. And then some people took advantage of that, the famous oligarchs, right? And then there was some level of re-centralization, and we're seeing that, for instance, in the structure of property in economies at Vietnam and all sorts of things. So the nature of decentralized AI is somehow here, practically speaking, is decentralized, but with certain what we call re-centralization vectors, right? With certain aspects of re-centralization. Now, today, we deal with large clients across different industries, mostly financial and hospitality, building deep learning and AI projects at scale, and 100% the nature of these projects is completely centralized. There is minimum level of centralization on that. Now, when we say centralized, that's not a single term that broadly encompasses the entire nature of an AI project. There are different vectors of centralization in AI. So when you think about how we share data, how we train models, how we deploy those models, all those mechanisms are completely centralized. So let me give you a few examples. So the data problem. A company has data that have accumulated over years of operations, and they want to start creating certain artificial intelligence models against it. So typically, that exercise happens completely within the confines of that company. And the richness of the models is particularly constrained by the richness of those data sets. So what if we could live in a world in which different companies could contribute to the same data set? So for instance, medical research. So what if different medical institutions could contribute to data sets that could advance medical research, but they can do that in a way that would preserve their privacy and wouldn't violate any of their compliance requirements. So the centralized model for implementing machine learning or deep learning models is also a big challenge. So today, you're a company, you want to implement a machine learning scenario, you hire a consulting firm or have a data science team. Internally, they built a model and deploy it. How do you know that model is correct? How do you know it's the best model for the problem that you're trying to solve? So at Invector, for instance, we try to play with almost competitions between different teams, trying to assemble models that compete against each other to try to arrive to the to the best solution. So what if you could live in a world in which a company would publish the data and different data science teams will sort of compete to try to produce models, and you can either pick the best model or actually use techniques like ensemble learning or transfer learning to assemble all the models into a complete model that is the one you're going to use. So there is a hedge fund in San Francisco called Numerite that uses this approach, right? They outsource competitions to data scientists about creating models that model trace based on certain market dynamics, and they test the models against live data in the market, and the models that work, they pick the top 4 or 5 and assemble them together in an ensemble model. They call it the meta model, and they trade with those models. We also have a centralization problems when it comes to training and the models itself. So a company, again, it wants to put together something, a machine learning model. They hire a consulting firm and they're responsible for training the model. How do you know that training was correct? How do you know when the model needs to be retrained? How do you hold the data scientists accountable for what they're doing? What if you could live in a world in which multiple people could actually contribute to train the model over time and they're compensated accordingly? And when it comes to regularizing or optimizing model, there is also a centralization problem, right? Typically, the same company that does the training, the implementation is the one that is regularizing the model. So even if the model, we think about this like a cultural level of overfitting, right? Like even if you're doing your best to not try to overfit because you're also responsible for optimizing and regularizing the model, there is a certain level of bias in terms of how you're going to approach that. What if you could live in a world in which multiple data scientists will publish a model to a network and they will contribute to the regularization and optimization of that model? Now, let's get a little bit philosophical about this, because I show you the technical challenge of centralized AI. How about the risk of this approach? So if we think about this from the point of view of economics and socioeconomics, there are different risks of what centralized AI could bring to the table. One is the rich get richer problem, right? Which was beautifully captured by Scott Galloway in the famous book, The Four, that sort of quantifies the influence of Facebook, Google, Amazon, and Apple, the influence that those companies have in the modern economy. So the rich get richer problem is a consequence of the fact that AI is mostly a privilege of companies that have rich data sets, either rich data sets because they have a lot of history, or rich data set because they have a lot of usage like Uber, and they have been able to amass incredible amounts of data in a very short period of time. So these companies have a lot of data. They create new artificial intelligence models. The models produce more intelligence and data, and then they get even better data. So what this creates is a very, very strong barrier of entry for startups. Even startups with a lot of talent in data science, they have a very hard time productionizing the models because they don't have the data. And in a centralized model in which the big companies control the data, then the rich are always going to get richer. Then we have the fact that knowledge is an intrinsically decentralized activity from the cognitive standpoint. So as humans, we build knowledge by capturing bits and pieces of many sensors during an interaction. So it's incredibly decentralized. And the analogy there will be the Wikipedia versus the traditional encyclopedias, right? But in a decentralized nature of AI, it goes against that decentralized nature of knowledge. So it's a single company controlling the entire life cycle of the process of building knowledge. Again, a book in this, obviously a book in this area is the famous Wisdom of Crowds. That was the first book that sort of depicted the crowdsourcing phenomenon from a cognitive standpoint. And then the transparency influence ratio. We're going through this in the United States with all the noise around the meddling in the last election, and you're seeing all these hearings in Congress in which big companies like Google, Facebook, and Twitter are questioning about the nature of their algorithms and how these algorithms are making decisions, and they don't provide a very an explanation in terms of that helps the public understand how decisions are being made. And we all know that interpretability is a challenge for AI, but what happens is that never in the history of mankind we have been in a position in which so many people can make have the power to make decisions that affects the general public without suffering the consequences. And this thesis was beautifully captured by Nassim Nicholas Taleb in his new book of this year called Skin in the Game, that talks about, why you should be accountable for the decision. So as AI becomes more centralized, these companies are amassing a ton of power, and they're really not liable for a lot of the consequences. So the obvious thing is, can we just decentralize the whole thing? And the answer is not so simple. I mean, it's not, even if it makes conceptual sense, there is a ton of barriers of entry for decentralized AI models. So here's some of the challenges that we see all the time when we try to introduce certain level of decentralization in an AI project. First of all, it's a privacy problem, right? We deal with this every week. We're working with a big company, and it's our first project. And then the question of how do we share data with you guys in a secure manner comes to the table. And then you need to introduce all sorts of end up signing a bunch of documents and things. But in terms of implementing a mechanism that enables the sharing of data without an implicit trust between the parties is really hard to do. The same applies for models, right? Can you distribute a machine learning, a deep learning model across thousands of nodes on which you don't really have and execute across thousands of nodes in an autonomous fashion? Then there is the transparency problem. You're creating machine deep learning models. How do you keep the different parties accountable? Who trained this model? What was the train? What was the score at that time? What did we report? Why didn't we improve the score? So how do you keep certain level of transparency and accountability across the entire process? And then finally is the economic dynamics of all the people that contribute to improve the knowledge of a program. How can they be compensated? And if you're in a centralized mode, these problems, they don't really exist too much. But the minute you move to a world in which there are all sorts of parties collaborating to create a machine learning models, these problems become at the front and center of your development. So there are a few trends that are influencing decentralized, the movement towards decentralized AI. The technology foundation of decentralized AI is relatively different from the traditional centralized AI mechanism. So among those trends that we're gonna be discussing now, there are many that deal with the privacy issue. How do we share data in a decentralized fashion while preserving certain properties such as privacy, such as compliance, without revealing and preserving sensitive information? So again, in a centralized way, well, this is not a problem because typically there are two parties and there's a bunch of contractual agreements. But the minute you extrapolate this to a decentralized world, these problems becomes very, very visible. So the first trend that can help here is homomorphic encryption. One of our data scientists was reviewing this slide deck yesterday and told me that I needed to use like analogies to explain all this complex mathematical stuff. So I'm gonna try my best to explain this in an easy way, because homomorphic encryption is one of those things that feels like magic. So conceptually, homomorphic encryption is a series of mathematical operations that you can perform over a data set in which you can actually obtain results without getting an understanding of the data. So suppose that Alice has a jewelry store, and she has a bunch of artisans that are creating jewelries, but she doesn't want to give her complete access to the precious metals because she doesn't trust them. So imagine that she creates this box in which somebody can manipulate the materials, create beautiful jewelry pieces, but they cannot take them. They cannot take the pieces out, even if they're seeing the entire work. So this is the nature of homomorphic encryption. This is an analogy of homomorphic encryption. You would take a data set and perform an encryption operation that will allow other parties to perform mathematical computations, everything that derived from addition and multiplication, which is pretty much everything, on top of that data, but they don't need to see the data set itself. So Numerai, that hedge fund I mentioned, they do that. They don't want to share the data set, the market data, with their data scientists because it's very proprietary and it costs. If you're done working Wall Street, acquiring those data sets costs a lot of money. So they use encryption techniques, not homomorphic, but the same concept that will allow the data scientists to perform computations over the data without actually seeing the data itself. Now, the obvious answer that we hear all the time when we present this concept is, why don't you anonymize the data? And while anonymization works in certain scenarios, it doesn't work in many others. So people can actually, if you give them a data set, let's say of Apple trades, the trades on the Apple stock, and even if they're anonymized, you remove the APPL stock ticker, most people can probably extrapolate that that's Apple by just doing some social engineering or looking at macroeconomic indicators or all sorts of other things. So a homomorphic encryption is this operation in which, suppose that you have an encryption function over two data primitives, A and B. There are two types of homomorphic encryption. The first iteration in the market is this thing that was called partial homomorphic encryption, in which given E on A and E on B, you can actually compute E on A plus B or E on A multiplied by B, but not both. So I can perform additional operations that derive from additional multiplications on top of an encrypted data set. And there are a few algorithms, that the unpadded RSA, which is the most famous one, and others that work on this technique. Performing both addition and multiplication algorithms was considered impossible until 2009, in which a scientist that works from the IBM Watson Research Group, Craig Gentry, in his PhD thesis, published a method for doing what is called fully homomorphic encryption, which is a technique that allows you to do all sorts of computation. Essentially, any deep learning model can be decomposed as a series of additional multiplication operations, and you can essentially execute an entire series of computations over a homomorphically encrypted data set without having to reveal the data set itself. So how would this work in a decentralized AI scenario? And then I'm going to show you some technologies that I'm doing this. So a company will publish a data set to the network of other companies. It will be homomorphically encrypted. The data scientists will download the data set and they can execute their models on TensorFlow or PyTorch or whatever without actually having to see to understand the semantics of the data. I hope that makes sense. If you have any questions for all, remember to use the chat window. So homomorphic encryption today, is it really viable? It's mostly a theoretical exercise. There are companies like Microsoft and IBM that are all over this. They're pushing the agenda, and there are open source libraries like Hilip that provide certain decent levels of partial homomorphic encryption. But for the most part, it's very expensive. And when I say expensive, I don't really mean like it takes a few hours to compute something. Like performing a basic algorithmic computation on top of a homomorphically encrypted data set of a few thousand records could take an entire year using expensive instances on Amazon EC2. So it's very, very expensive. Today is really not practical. And you're going to hear companies out there claiming that they're using this stuff. For the most part, is in a lab environment. It doesn't really work mainstream. So there are alternatives to that actually work. One of them is this thing called adversarial neural cryptography, which is related to Ian Goodfellow's talk in the next hour. So GANs, right, are adversarial networks, are networks that compete and collaborate to build better knowledge in an environment. It was a concept introduced by Ian Goodfellow and other people in 2014. Known as generative adversarial neural networks. But the interesting thing is that GANs can also be used for neural networks to learn better cryptography mechanics without actually knowing a whole lot about cryptography itself. So how would this actually work? So again, to give you a simple example, this is a canonical example for GAN cryptography. We have two neural networks, Alice and Bob, that are trying to communicate securely, and we have a third neural network, Eve, that is listening to the communication and trying to break the encryption. So Alice and Bob will start with very simple encryption mechanisms, sharing a private key, and Eve will progressively try to break that encryption. But as Eve, the findings of Eve are factoring into the algorithms that Alice and Bob are using to communicate. So essentially, over time, Alice and Bob learn to defeat the best version of Eve. The way this works technically is that the algorithm, the output of Eve is factoring as the loss function of Alice and Bob, technically speaking. So over time, if you see the chart for GAN cryptography at the very beginning, Eve does a very good job trying to break that the secure communication between Alice and Bob, but over time it becomes impossible. So these are networks that essentially build dynamic cryptographic primitive over time by just competing against each other, and it's a super hot trend that is really not that hard to implement, and there's very practical applications of it. So how would this work in a decentralized AI scenario? So a company will essentially establish a secure channel with the data scientists using adversarial neural networks, and the data scientist could be a single consulting firm. And they will have other neural networks that are trying to break that communication, and then the encryption mechanism itself will be dynamic. Going back to the Numerai example, this is actually the technique that Numerai uses. It's not homomorphic encryption, but the team that built this, Numerai hired a few of the data scientists from DeepMind, and this is a technique that they actually implemented for sharing data with the data scientists. So GAN cryptography is very new. It's a research area, but you can find practical implementations already that work decently well. And then there is a third trend in terms of privacy that we like a lot. It's called secure multi-party computations, and this one is very practical. There are some very accessible implementations of SMPC in the market today. Now, let me give you another practical example of this. So SMPC solves a similar problem to homomorphic encryption. So many people are interested in computing a specific information, but they don't want to reveal a specific data set that they own. So the traditional problem for this is called the millionaires problem, in which you have a group of millionaires that are interested in knowing who is the wealthiest of them all, but they don't want to reveal their net worth. So what they do is they exchange a mathematical function that based on their net worth, traditional and addition between the different networks, between all of them multiple times, and eventually you can arrive to the answer is to compute who is the wealthiest of them all. There is another example is two people go out on a date, and they want to know if they will follow up, they will go on a follow-on data, but they don't want to say it. So they use a specific function that exchange information between the two that allows them to infer if they would like to go, if they will both like to go into to a next day. So how does this work? More mathematically speaking. So you have a series of parties. They want to compute a specific join function based on all the inputs without revealing those inputs themselves. The traditional approach is you trust an intermediary, right? All the millionaires trust a third party that will get on their net worth and sort of communicate who is the wealthiest of the group. But obviously that has all sorts of privacy implications. So SMPC, what it does, it allows to compute this function by just exchanging information between all the different parties. In the context of decentralized AI, it will work very similarly to homomorphic encryption. So a company will use SMPC to secure a data set and publish it to a network, publish the computed function to a network, which means an operation on top of the data set, and then the different nodes on that network will execute exchange messages based on an SMPC protocol. Now, there is an implementation of secure multi-party computations for blockchain technologies called Enigma. It came out of MIT. It addresses many of the issues with blockchains like Ethereum in terms of scalability and privacy. So that's our mantra: private and scalable computations, and it uses SMPC underneath, and it's incredibly scalable. You can check it out on enigma.co. And is at least in the lab environment, it seems very, very promising. And there are several implementations of SMPC out there. So these are some of the techniques that you will use to solve the decentralized privacy issue, meaning how do you exchange data in a decentralized network without having to trust other people. Now, how about learning? How do you solve learning in a decentralized fashion? Meaning you have many nodes on a network that need to learn at the same time, and they don't want to do the traditional approach in which all the knowledge is owned by a central server. So the traditional approach to this, the traditional scenario for this is mobile. We have billions of devices out there. They're computing, they're executing AI models for different things. The traditional approach is they're calling APIs in a cloud data center and obtaining the results, but obviously that has two issues. One is scalability and latency. So it's really hard to execute machine learning models real time in that fashion, and the other one is privacy. So the whole point of using AI is that it gets better over time. To get better over time, it has to learn from your data, and obviously that has a privacy implication when you're dealing in scenarios with personal data. So the approach here is a technique that Google recently pioneered called federated learning. And federated learning essentially allows to execute a model in a distributed network of nodes and then compute the improvements of that model across all the nodes and then distribute new versions of the model. So essentially, in the first step, a centralized authority will push a model to the different nodes. Think about your smartphones. The nodes would run your image recognition model or whatever would run locally on your smartphone using technologies like TensorFlow Lite or something like that. The gradients of that model will be computed using a stochastic gradient descent or any optimization mechanism, and those gradients will be pushed to the centralized server, not the information, just the gradient. The centralized server will recompute and retrain the model and push new versions of the model to the servers, and it will repeat that over and over again until you achieve certain level of convergence, until the models become really, really performant. So how would this work? So actually this works, right? We are using this on a couple of scenarios. The Google research on this is very compelling. So there is a federated approach, that is what I just illustrated, in which you have a centralized node that controls the training and distribution of the model, or you can go for a more decentralized approach, like some of the blockchain technologies that I'm going to show you at the very end, in which all the nodes are exchanging this information. But the nature of this federated learning approach is relatively simple to implement, and it actually works. It's so simple that you're probably using it today if you're carrying an Android phone. So Google Gboard is actually based on federated learning scenario, and there are libraries for doing this in TensorFlow like today. And again, when it comes to distributing learning, achieving learning across a distributed network of nodes, is a very practical approach, and one that is relatively simple to implement. So now the last part, the last two parts, right? How do we run this thing, right? Like we have the models that we wanna run in a decentralized network. How does that work? And this is where blockchain technologies come to play. How can you execute computations, machine learning computations in a network without having to trust a centralized authority? So I don't want to bore you with obvious details, but this is the nature of blockchain technologies and smart contracts. So blockchains are distributed ledgers that can execute computations without trusting in a trustless fashion, right? Trust is built mathematically into the network, but there is no implicit trust between the nodes. And smart contracts is the way in which you express code in the blockchain. So it started with technologies like Ethereum, and obviously now there is a million blockchain technologies that have support for smart contract languages. So Silica, Stellar, Enigma, there are plenty, right? So this is a way that you execute code, that you write code that executes in an immutable, transparent fashion on the blockchain. How is this related to decentralized AI? Well, we can think about this workflow that obviously I took this from some of the decentralized AI experiments that have taken place out there. So a company will publish a data set to a blockchain, a smart contract. Data scientists can download that data set by invoking data smart contracts. Those data scientists can build and train models using their favorite deep learning library. They will publish the model via different smart contracts. Then another data scientist, which could be the same, will download the model to test and optimize it and publish the model again to a blockchain, and the company will use that model. And obviously all these interactions are tracked immutably in the blockchain. So at any given point, we know who trained what was the result, what was the technology, what were the optimization techniques, how did it evolve over time, and that's there, and it's immutable, and nobody can dispute it. And at no point there is an implicit trust between the company and the data scientist. It's all enforced via blockchain technology. So this is the nature, this is the core of decentralized AI technologies today. Every company that is trying this in the real world is building an architecture that in some form or fashion resembles this diagram. Now, this comes with another problem, that is the incentive problem. If you're in an enterprise scenario, this is not such a big deal. Because obviously you hire an agency or a consulting firm like in Vector Labs, and they know there is a contract, and you compensate based on that. But if you're doing other things like a Kaggle model, in which you're outsourcing the creation of a model to multiple competing parties, and you extrapolate that to not only the creation of the model, but the training of the model, the regularization of the model, and all those things, how do you compensate the different parties to based on their work they perform? And the obvious answer here is using crypto tokens. So by now, everybody's familiar with the fever around initial coin offerings, ICOs. There is a new trend now this year called security token offerings, STOs. But essentially, the idea that you can create a token that injects cryptoeconomic primitive into a software applications is a very compelling scenario, not only for fundraising and things like that, but for compensation mechanisms. So the most famous standard for crypto tokens is the Ethereum ERC20. That's the one that most companies that are doing building their own tokens follow. And the model here is exactly the same diagram that I will that I show you before, but at the very end of this, the tokens will get issued to the different data scientists. So I'm a data scientist. I take a model from the blockchain. I perform training. The training score well. I receive tokens in compensation for that work, and that because you start building, injecting an economic engine into your own decentralized AI architecture. So all this seems very futuristic. I love this quote from William Gibson that said the future is here, but it's just not even evenly distributed. So this is happening today. It's not fantasy. It's not research lab. There is a series of decentralized AI platforms that are bringing this promise to market. Let me give you an example. SingularityNET is arguably the most famous one of all, because it's the one that powers a famous Sophia robot. That, you know, if you follow Silicon Valley, the TV show, that when they show Sophia and they show this company that Pied Piper that is doing a decentralized internet, well, the analogy here was was SingularityNet. That's a network that powers Sophia in the real world. They're building their own blockchain technology. They have a number of technologies out there, like a decentralized application marketplace that are applications based on the blockchain. They have a registry for all the services that organizations can use. You can download and use the specific versions of SingularityNet, and it's still very early. But they already have partnerships with big enterprises trying to implement this model. Another company I like a lot, it's not a company, it's more like a community, it's called OpenMind. So OpenMind got started by a couple of researchers from Oxford University, and essentially it's a community of data scientists that are collaborating to build decentralized AI architecture. So all this primitive that we talk here, they're building. They have a library for homomorphic, partial homomorphic encryption. They have a runtime that can work on different blockchains such as Ethereum or EOS or other. They have a mechanism based on IPFS, that is another blockchain technology, which you can share data in a secure way and things like that. One of the most practical applications of decentralized AI came from Algorithmia, the startup from Seattle. And they implemented this protocol called Danku, and they actually ran a data science contest using Danku, in which they essentially push a data set to the network using that smart contract, and then data scientists downloaded, they run the computations, they submitted the models, and then Algorithmia issued tokens to award the winners. This happened about 3 months ago, and it's one of the first practical applications of decentralized AI today. And it was I spoke to the team after this, and it seemed that it was really, really successful. There is another technology that has some traction in the space called the Ocean protocol, and Ocean essentially builds a decentralized model for data sharing. So it allows providers to submit published data set in a secure manner to a marketplace, and it allows consumers to download those data sets via specific interfaces, and has a network of they call keepers that are responsible for maintaining quality on the network, and they have incentive mechanism based on crypto tokens to compensate the keepers. So those are some of the arguably the four most popular decentralized AI implementations in the market. So let me summarize this real quick and switch back to video. The future of AI is likely to be more decentralized. We're not there yet, but you're seeing the trend. So it's happening slowly, but trends like blockchain and the advances of cybersecurity are pushing this. In order for this vision to materialize, we need three fundamental building blocks. We need a decentralized runtime to execute computations. That's blockchains. We need decentralized learning methods such as federated learning, and we need a lot of privacy to exchange data, and that's what things like homomorphic encryption, GAN cryptography, or secure multi-party computations are going to give you. Definitely, blockchain is the biggest catalyzer here. Many startups are looking at the intersection of blockchain and AI. We talk to a lot of them. We test a lot of those technologies. So this is happening already. So that's all I got. This is my information, which I'm sure the conference organizers already shared. You can drop me an email to jr@invectoriq.com. You can drop me an email through Medium. I write about AI almost every week, multiple times a week. Or you can follow me on Twitter. Thank you very much for joining. I hope you enjoyed the talk. I hope I didn't scare you too much, and you're gonna attend my next talk at 3 p.m. that we're gonna talk about practical lessons for scaling deep learning applications. That one, as theoretical as this was, that one is gonna be very practical. So I hope to see you there. Thank you very much.